one question to answer. Are there any questions?
Our final is the Wednesday after.
Yes.
Yeah, it feels like every semester you play this class next Monday, and then I thought Friday would be the Monday after that. Because we had too many holidays. Like every semester the Mondays, the classes always get pushed one day. Is he gonna go over 6 months?
Right. Our topic for today is congruences. And I will rush the first page of the notes, just commenting. I'm not going to write too much on the board for a very simple reason, to save time. And I hope you will get an idea of what's happening. But I'm not going to go too much into formalities. I'll just give you hints at how to read the notes. But if this doesn't make sense, just what do we do here? Congruence relation is the one that we already studied in section 3. So it says the following, we did it modulo 6, so we say the following: A congruent with B modulo N, if and only A, their difference is divisible by N. That's the definition. So for example, you ask me, is 7 congruent modulo 8 with 15? Yes or no? Then how do we answer that question? Always in mathematics, definition has new part and the old part. So always translate it. Say, this question means basically the same as does 8 divide 15 minus 7. Yes or no? Yes. So your answer is yes, they are congruent. Is that clear? And then here comes a very important statement, but I'll skip proof completely. It's fairly easy to prove it and check it. So A congruent with B has this meaning that we just outlined on the board. But it says equivalent to this are two other formulations of this statement. What are they? That B equals A plus certain multiple of N. Do you agree? Because then obviously their difference is divisible by N. But this is like more equation than relation. And what else? My favorite is actually number 3. What is it? If they give you the same remainder, then they are related. Don't you agree? Because when they give the same remainder, that means both they exactly differ by K. So if you want to check if, for example, 35 is congruent with 7 modulo 4, well, what can you do individually? You don't want to subtract them, but somehow you know that a remainder of 35 modulo 4 is what? When you divide 35 modulo 4, what's your remainder? Is it 3? Mm-hmm. What's the remainder of 7 modulo 4? What is the remainder? Do they give the same remainder? Are they congruent? Because everybody is congruent with its remainder according to section 2. So that's the story about this relation that we discussed last time. By the way, this is an equivalence relation. Do we have equivalence classes? Yes or no? And how do they look like? Because number 3 tells you the only thing that matters is your remainder. So what are the possible remainder? If I do modulo 10, what are the possible remainders? Are there those that have remainder 0? Yes or no? And whoever's there, and modulo 10. So is there another one?
Yes,
1, 2, 3. The last one is 9. Does everyone fall into one of these classes? Yes, because quotient remainder theorem says n is 10 times q plus r, where r is between 0 and 9. Less than 10 is between 0 and 9. Do you agree with me? So that's the summary of this equivalence relation, where you actually reduce every number to its remainder modulo n. But even better thing than this is, from that splitting, is the following. And I commented about it a little bit, but now let's see it as a formalized statement. It is this theorem. Second proposition tells you the following. Can someone read 1 and 2 and interpret what they are? If A is congruent with B and C is congruent with the D, then what happens? How would you say this in one quick word without too much formalism? Does congruence behave like equality? Is that the property of equalities we always use to solve equations and whatever? So add left side and right side of the equation. Are we allowed to do that here as well? And what else? Can we multiply them as well? So generally, algebraically, we can act with those congruences the same way as we act with equations or equalities. And then here's a little proof. As I said, it's more exercise in proving than anything kind of complicated or and here's a very nice example. I'm asking this example, we are asked to do the following. Example. Calculate 675 to 307 modulo 713. Any comments? So the answer should be, we always say that, maybe I didn't explain it precisely. When we say calculate, we mean in which of those, how many of those classes do I have? Do I have 713 classes? So which class will this number be in? You might say, oh, in his own class, but please describe it according to the remainder, because then people will understand it the best way. So, or I could have asked that question, what is the remainder of this number when I divide by 730? What is the big obstacle?
The giant.
Can you imagine how huge it is?
675 is what you need to
What's
worry
it?
about. 675 is the only one you need to worry about, right?
Oh, but also 307, because it's not 675 to 1, or to 3, 675 to 307. But they both influence these. So the question is, how can I calculate this quickly? Sometimes there are certain tricks that can help you to do that quickly. But let me show you one general algorithmic procedure. It doesn't look short or quick, but you can do it, I don't know, quite fast. Here it is. You start calculating square, even powers of 2. 675 square. What about that? Can I get the remainder using calculator? Yes or no? How do I do that? Either you have a little program that calculates remainder, or you improvise it, and here's what I'll do. 675 squared. I'll take this and I will divide it by what? 700 and? What did I get? 639. Unfortunately, this remainder is not in the fractional form. Do you see that? So what should I do? But I know the quotient is 639, so I can do the following: 675 squared minus the 639 laps times 713, because that's a quotient. And I get my remainder. So what's the remainder? 80. get raise 675 to the fourth, who will I raise? 18 to the square. It's congruent with 18 squared. Are you sure that they are congruent? Yes, that's because of the theorem. I just use this and square both sides. Who is easier to calculate, left side or right side? Right side obvious, 18 squared is just 324. I don't even need calculator for that. And that's within 0, 7, 30. Now I go what? 675 to which power? 8, which is congruent with what? 324 squared. My last result squared. For this one I cannot do it by hand, but we'll do for the same story. 3. Why don't I? No, it's not good. 324 squared divided by 713. So what's my remainder? 0.23 so on. But what do I do now? 324 squared minus 730 times 147. What's my remainder? 165. Only 675 to the 8 is quite a huge number, quite a big number. But this way, I'm just squaring and reducing, and I can get higher and higher power. Do you understand the pattern? So who is the next one that I calculate? You don't sound too enthusiastic. I lost it somewhere. Does it make sense what I'm doing or not? Not. Okay, so once again, I know that I need 307. I'll show you how to do 307. But what I'm doing here, I'm just doing powers of 2. 675 to the square, to the 4, to the 8. So I'm just, whenever I reduce modulo 713, I then square both sides. And then I get higher and higher power of 675. So for example, right now I guarantee that 675 to the 8, when you divide it by 713, it will give you this remainder. And then what? I go into higher and higher. What about 60? Can I get that one? I square both sides. So that would be congruent with 165. What? Square. Which is how much? How much is that when you reduce it? 165 squared. Divided by 730. You know what is the other? I don't know if I know how to do it. There's an alternative way if you like it more. Remove 38. Here's my remainder. Do you agree? But this remainder I like in the fractional form. So there is a feature of calculator that yes, reduce that into fraction. It is 131 over 713. If you like more this flow, that's okay. So this is congruent with what? 131. And then I will use from my notes the other powers because I don't want to repeat automatic process now 10 times. I went all the way to 131. Now I take what, 675 to 32. It's congruent with 131 squared, which will give me 49. Then when I take 675 to 64, I get 49 squared, which will give me 262. 675 to 128, which will give me, when I square this one now, 156. And then 675 to 56, that will give me 627. What happens? So what this says, if someone's making, 675 laps, so what would that be? 675 times. So why did I stop at 256? Because that's what I need for 307. And here's the trick. Now you represent 307 in the binary. So what is 307 in terms of powers of 2? I'm not going to write binary. So that's 256 plus what? What's left? 51. Do you agree with me? But then 256 is what? 51 is what? 32 plus 19, which is what? 16 plus 3, which is 16 plus 2 plus 1. Do you agree with me? So what is that tell you? Here they are. Look, not mine. Here they are. So I can say the following. 675. 307 is congruent to 675. All right, let me write a little longer. 256 plus 2 plus 1. You get me? And then rules of arithmetic tell you, can I separate these powers? But instead of plus, what will I get? 75 times 675 Is this all correct? But now what? Do I have all of them reduced? So what it tells me is who to take. Yes. 256. Who else do I take? Which is 49. Who else do I take? Which is here. And 2 and 1. Okay. I mean this circle for 1. So here it is 2 and then 1 is 675. So we'll say the following congruent. So with 627 times what? 49 times 131 times 324. What is circle 324? Is there a reason? What's wrong? I don't need 4 power. What? No, just that it's clear. 131 times what? 18 and times the original 675. Here it is. When you multiply these 1, 2, 3, 4, 5 numbers, again reduce modulo 713, and then when you do that, the result is congruent with the 3 modulo 713. And that's how this calculation goes. Yes.
So, the 675,
Is because 675 to 1.
okay, I got it. That's the remainder.
Yes.
In the
So
7.
that's what
Isn't that we're looking at remainders, right?
this is. 3. No, 675 is its own remainder. So not, I don't know.
Yeah,
I can
that's-
even
that's
calculate.
what
I didn't even put it on the board, but if you want 675 to 1, it's just 675. Because you always, what if that number was bigger than 713? 713, I would reduce it, of course. I think this makes sense only for numbers below. Otherwise, I would reduce the base. But the base was reduced, but still quite big, exponent big. And generally, here is the way to do this calculation. I don't say it's quick, but much easier than if you would calculate the whole number. This is like, you're doing calculation within your memory. And then whenever you get a big result, you reduce it and then make it accessible for your toolbox. But on the other hand, this algebra guarantees that this is all correct and that you're really getting something that's congruent. And of course, one thing should be always emphasized, but is that number equal? No, but they are congruent modulo 713. Why would you care that they are congruent? Sometimes congruent things, we think of them as being the same for whatever we need. So sometimes it's important to find the position up to some certain module, and you will see a couple of nice applications. So what did you learn in this example? We learned how to apply this theorem to calculate remainders modulo for some huge numbers. And then next thing that we want to discuss is understand the question? So I'm asking you to find the number x between 0 and 659, so that when I plug it in and reduce modulo 660, I'll get 1. 43 times 1 is 43. You're going to get 1. So first, of course, there is one. What if you had this equation, 7x equals 1 among the reals? If I asked you to solve this, would you be able to do it quickly? Yes or no? Yeah, just say x equals 1, 7. That's reciprocal. That's the story of reciprocal. And that's why reciprocals were invented. Actually, rational numbers were invented so that we can solve equations like this. Here, I don't want to invent the new numbers. I'm sure that there is an integer that will satisfy this. Is there a way to do it? Can I write a program and just plug in all the, because this is finite, because there are how many possible candidates? 0 to 659, 660 candidates, agree? Can I write a quick program to check them and then identify who's going to do it? Yes, that's not too complicated, but the question is, can we do it in a faster and more efficient way? And the answer is yes. And that's what we want to analyze. How do we solve this type of equation quickly? The key ingredient is that these two numbers, 43 and 660, are relatively prime. So 43 and 660 are relatively prime. If they are not relatively prime, you cannot do this. There's easy proof that that cannot be done. Are relatively prime. That means what? That GCD of 43 and 660 is what? No, GCD is just 1. No, not the least common multiple. GCD, greatest common, they don't have common factors. That's what's relatively prime. So what then? What is crucial here in that fact that GCD for 43 and 660 is 1? When we run Euclidean algorithm, remember Euclidean algorithm? At the end of Euclidean algorithm, we do get GCD. So in this case, we'll get what? 1. So here's what happens. Run Euclidean algorithm. So what do? I take 660. I divide by 43 times what? Can someone help me with this division? Calculator? Oh, for sure. convinced that you have a good idea. I'm not willing to do this, of course. What's the next step?
Move everything to one.
So this guy goes out, these two continue. So 43 equals what? 15 times what? 2 plus 13. Then 15 and 13 go. What? 13 times 1 plus 2. Oh, continues forever. 13 is what? 2 times 6 plus 1. And finally I'm done. That's because then 2 equals 1 times 2 is equal 0 stop. Here's your Euclidean algorithm. Do you agree? Then what happens? You can think of this as some timeline, like predecessor and ancestor or ancestor. So who was in the beginning of the story? Who's next one? Who's next one? Who's next one? And then 2 and then 1. Agree? And here's the idea. At the end of the story, I want these two numbers to appear. I want to express 1 as what we call linear combination of those two upper ones. But you have to go step by step, recursively. So here it is. Can I express 1 as a function of two predecessors, yes or no? How? Move 2, so we got the full name. 1 equals 13 minus 6 times 3. And circle those and then never multiply out. Leave those like boxes. So who are the players on my right side? 13 and 2, do you agree? Now what? Who is younger among them? Lower in the rank? 2. Get rid of 2. How do you get rid of 2? Use the previous line. So it would be keep 13. 13 is okay. How do you express 2 from this line now? This is the line. Can you express 2 using 15 and 13? As what?
15 minus
15 minus 13. Put them in the box so that you don't get tempted to multiply out. That's not a good idea. Can I now distribute this? Yes or no? I mean distribute this 6, but don't distribute inside. So it would be 13 minus what? 6 times 15 and plus 6 times 13. I'm doing this if you have linear algebra. These are my base vectors, base system. So what would it be then? How many 13s do I have?
6.
And one more in the beginning, so how many? 7 times 9 times. Do you understand the idea? So who's now on my right side? Is 2 gone? 2 is gone. Who are the players now? 13 and 15. Who do we eliminate now? 13. In the line where 13 was the remainder. And this is the line. What about 15? 15 is kept for a while. So I'll continue. Oh, by the way, in this calculation, on every line you can check your calculation. 7 times 13 is 91 minus 90. Am I getting 1? So I didn't make any calculation. So on the next line, what do? I put 7. I trade 13. How do I trade it? I trade 13 using this line, or I trade for 43 and 15, so it would be 43 minus 2 times. And then minus 6 times 15. So what do I get here? 7 times 43 minus 14 times 15 minus 6 times. So do I get all together?
7 times 43 minus
20 times. Check your calculation. 301 minus 300 is really 1. So I'm making 1 in a more and more complicated way. Progressing up that timeline. So what now? So 13 is gone. 43 and 15 are the players.
get rid of 15.
Get rid of 15. How do I get rid of 15?
16
exactly first line. So it's 7 times 43 minus 20 times 660 minus 43. Really? What would that be? Be careful with the calculation. It's 7 times 43. Never distribute inside the box. Boxes must be intact. Minus, how many times 43? Be careful, there is 20.
Plus.
There is 3 plus, thank you. How many? No, 300. 20 times 15 is 300 times 4.
Minus 46.
Which I guess combined 43 is 307 times 43 minus 20 times 660. Of course, if you put this in calculator, we should get 1. Can someone check for me? Works, so what did we accomplish? We say that we represented the 1, which is GCD of those two numbers. We represented it as a linear combination of 43 and 660. That's called Bezout's theorem. Second visit, because you had one in calculus. Bezout's theorem. There is one for polynomials. All right. So why is this answering this question here? Because here it is. This equation says 1 equals 307 times 43 minus 20 times 660. I just copied that calculation. Now I'm doing modulo 660. Does this matter modulo 660 or these are just whole laps?
Whole lap.
So that means modulo 660, this could be crossed, and I get the 1 equals 307 times 43. Did I solve the equation?
Yes.
Who is your x?
Yes.
307. So this procedure gives you the inverse. So really, if you do 307 modulo, 307 times 43, you will get 1 modulo 660. By the way, if there's another number, there is a theorem saying no, this solution is infinite. So there is one number. So what is the summary of this? If your module and your coefficient are relatively prime, then there is a solution, and that solution could be obtained using Euclidean algorithm. What if they are not relatively prime?
You can't use it.
You can do it. Why? Because that number behaves somewhat like 0. Because can you solve this equation? Can you solve this equation? Why? Because 0 doesn't have an inverse, doesn't have a reciprocal, do you agree? The same way, if you want to do like this, 2x congruent with 5 modulo 8, that's not going to work. Why? Are they relatively prime? What's their GCD? 2. 2 does not divide 5. The same way as this is 0 does not divide 7. This GCD. So it kind of has some instances of 0 in itself. That's why it cannot be solved. So that tells us a little bit about it. So once again, if your module is relatively prime, if your coefficient is relatively prime to the module, you can find the inverses. And that's a question you can expect on the Wednesday of the exam. I know it's a little short time, but I don't think that it's too complicated. So this is the way how you get inverse. Just run Euclidean algorithm and go backwards with the substitution. There are 2 things to keep in mind. One, have this timeline so that you control how well you are progressing. Never multiply within the box. If you multiply within the box, you understand that? Because you don't know then who to replace. Boxes are like your basis vectors. All right. What else do we want to see here? Our next goal GCD of A and B is D, then you can get D as a linear combination. So the way I showed it for 1, does it work for any other number? Yes, as long as that's your GCD. GCD always can be recovered backwards through this Euclidean algorithm procedure. And this is the corollary that we said. If GCD of AN is 1, then there exists B that is your reciprocal. So if you are relatively prime to modules, then you have reciprocal. And then here is that example that I did. All right, one more theoretical statement, and then we will be ready to do one idea of a very simple encryption using the congruences, and it will show you a very nice application of congruences. In this theorem, particularly first one is a very famous theorem in number theory, and in many applications in computer science as well. So second one is less, is just consequence of that one. So what is the first one tell you? It's well known as so-called little Fermat's theorem, or Fermat's little theorem. So here, part I. Says the following. P is a prime number. I'm just writing here half of it here. So P is a prime number. And A is any number and not divisible by P, which is very mild assumption. Then what happens? If you take A and raise it to P minus 1, you will get 1. Modulo P. This is true only for prime numbers. To illustrate what is this doing is the following. Now, let's assume that P is 17. And if I take 12 to the 16, and I want to calculate modulo 17, how much would that be? Do I need to calculate it? Because you remember, it took us a while to calculate the remainder in the beginning of the class. Here, I don't need to bother. As long as this number is prime, and this is for 1 less, then automatically we know that that remainder is 1. So, you can say, so what? First, it's very nice in big calculation if you have something. Example, another example. Why is this important? Why is this useful? What if I want someone ask me 12 to the 379? Modulo 17. Yes, you don't. Can I run that algorithm that I started in the beginning? Powers 2, 4, 8. Yes, I can, but you remember how long it took me? But what about this? Can I reduce this modulo 16? So now you see, I'll do the following. I'll do 379. And I divide not by 17, by 16. And that will give me 23 and something. So what would that be? It tells me that 12 to the 379 is congruent
.6875 times 60 is
11 you said?
11.
Yes. All right. So what then? Do I need to calculate this part or not? Because I can say that this is 12 to the 23 times 60 times 12 to the 11, which would be what? 12 to the 16 23 times 12. How much is 12 to the 16 according to Fermat's theorem? 1. So the only thing that I calculate is which one? 12 to 11. Oh, this is all over. And then 12 to 11 is much easier. So generally, if you go above your module, and if your module is prime number, this is a very powerful trick to reduce very quickly your exponent. Yes.
So this just replaces what you showed earlier. That long way of doing this.
If you're dividing.
Yes, exactly. Yes, but
As long as
but
that's
no, no,
prime number.
but a disclaimer. In that example that I did in the beginning, let me show you. Why didn't I call it then? Why did I torture you with that
That's
long
not a prime
calculation? Because the exponent didn't exceed the base. You know, this is only.
Okay.
Let's
Oh,
look
yeah.
at that example that we had in the beginning, because I thought maybe to wait a little bit to show you this trick, but here it is. 675 to 307, so because 713 is probably a prime. So basically, if this was to 3070, I would reduce it using little Fermat's. But when you are below P minus 1, then it
Doesn't
doesn't
work.
count. Yes. But the combination of those two ideas would be, yes.
I was about to ask, so you can use this one after you've done that.
Exactly. Like here, 12 to the 11, however you want to do it with the first algorithm. What else? This is also, actually, it's an interesting thing that's a little bit away from what we're going to talk today. It is, you know, one of the big things in computer science is so-called primality testing. You have a huge number, and you want to test it if the number is prime. And you can follow that story on the internet. There was lots of excitement about primality testing. Usually they do something for Mersenne primes. And there's a history of checking the primality of those primes and algorithms to test them. And for a while, I think I told you this story, for Mersenne prime, those are the numbers of this form. 2 to the p plus 1. And then where p is a prime. Though they are not always primes. They are rarely primes. For some p's, they are primes. And people wanted to know for which p's does that happen. And so far they found like 40 of them, and they are like 2 million digits or 10 million digits. And when you look at the history of Mersenne prime, you can see the following. In the 60s and 70s, you have exactly how was 16th Mersenne prime invented? Using Lilac machine. 17, using IBM Cray 1 and Cray 2. I don't know if you remember those machines. Those were huge, big supercomputers in the old times that were able to actually run this huge number of operations and test if number is prime or not. And now they are not doing it with the super machine. They are doing it to parallel programming. So if you want to become part of it, you can devote your extra time of your computer when nobody is using it to be part of parallel computing process all around the world, where actually people test the newest Mersenne prime. And that's why recently, you know, like Mersenne prime number 16, Cray 1, 2, big lab, Cray number of Mersenne prime number 38. Australian high school student, John, you know, something very, very insignificant. Someone just happened on his computer or her computer that part of parallel programming was finished. One way or the other, I wanted to tell you the following. So testing if number is a prime is a huge thing. By the way, that's also how they test how fast is your machine. They just say, how fast can you check for I don't know, for example, 20 Mersenne prime if it's prime or not, to run that primality algorithm. And primality algorithm uses essentially base is A. Is the converse true? If you take a number Q, a number I don't want to make mixed up, is the converse true? For example, you test 2 to the U minus 1, you get 1. 3 to the U minus 1, you get 1. 4 to the U minus 1, you get 1. And all the way from U to the minus 1 to U minus 1, you get 1. Does that guarantee that number is prime? The answer is no. There are some numbers, they are called Carmichael numbers. I forgot what was the first one. That pass all the properties of Little Fermat's theorem, but still are not prime. They are false primes. And they are very rare, but we know that they exist. So generally, primality testing, this test is heavily involved in some other more serious primality testing algorithms. So that's another thing why it's important. What else is important about this one? For finding inverses. Why? Because, and another application. Suppose that I want to solve the following equation. 7x congruent with 1 modulo 7. I'm doing it on a purpose with a small number. Can we solve this? 7x congruent with 1 modulo 17. Yes or no?
Yes.
How? The way we explained it a minute ago. But you know what is the alternative way? Here it is. How much is 7 to the 16th? What is this theorem telling you? 7 to the 16th is for sure congruent with what? 1. So what is it telling you? 7 to the 15 times 7 is congruent with 1 modulo 7. Don't you agree? So who is that inverse? 7 to the 15. So if you can calculate quickly 7 to the 15, you don't have to run Euclidean algorithm. So Little Fermat's theorem also gives you a nice alternative to find an inverse. Just one lower, p minus 2. A to the p minus 2 is inverse of A. So that's another way to do it. I wrote an idea of the proof. Why is that theorem true? It's a very interesting proof as well. It goes along some properties of modular arithmetic, but I'll skip that one so that we can come to the application. Part 2 is just a variation of this theorem. So it's less fandious, but it's just easy consequence of this theorem. So what is it? It's kind of a variation of this theorem. So it's not 1 prime. How many primes are they using here? 2. And A is again any number that's not divisible by both. So it kind of doesn't work like double exposure in the Little Fermat's theorem. So what do? It says if you take A and you do modulo PQ, where P and Q are 2 different primes. Then to get 1, you need to raise it to what?
P minus 1.
And then to what?
Q minus 1.
Because first, when you raise it to P minus 1, that will make it 1 modulo P. Then when you raise it modulo Q minus 1, it will make it 1 modulo Q, so it will be 1 modulo P. So it's very easy to prove if you know the basic. But this is the theorem that we will use for encryption algorithm that I want to show you now. Here is the cutoff line for what could show up on the exam on Wednesday. So the example of encryption I won't put on that exam. It's just too much needed for that. But generally finding the inverse or something around Little Fermat's theorem, that's a legitimate candidate for the exam. But the encryption itself, that will appear on the final. Is that clear? So, here's how encryption algorithm, one nice encryption algorithm goes. So what are the encryption algorithms? now that coded word goes through an unsecure channel, through the air, through computers or anything, and goes to your receiver. And then what happens? The receiver really doesn't get, so this is the sender, he has a word, he codes it, sends it to a secure channel. And then when receiver gets the word, it doesn't get the original word, it gets what? Encrypted or coded word. Then receiver has decoder that's sent to a secure channel, and then that decoder does the following: takes C minus 1 of C of W, and you get W back. That's the idea of coding and decoding. And then, but of course, you want to find the coding that's not easy to break, so it's not easy to find the inverse function of your function. And then what? One of the most famous was Caesar coding. So what would that be? Yes. So for example, the way they label code, you kind of label each letter with a number, like numbers from 1 to 26. And then what do? You just add, for example, 3 to every number, and then instead of getting letters or A, B, C, then if you have letter A, then instead of A, you will write a letter that's 3 steps later. It will be D, and so on, so that the word that's intercepted doesn't make sense, and then your receiver knows that they should subtract 3 and everything. You agree? It's very simple, easy to break, and so on. Oh, by the way, how would you break that if you don't know the code? How would you break?
You can just try 26 possibilities for breaking each.
Okay?
You can just try 26 possibilities.
I agree, but yes. So one of the main tricks,
Just look at the frequency of the letter.
frequency of letters. That's one of the main tricks. So you know that, for example, in standard text in English, let's say A appears in 4.3% of all the letters on an average page, and then you suddenly an F appears in 1%. Suddenly you see your F repeats 4.3%, and you say, oh yes, that. So according to the frequencies, not 1 page, 2 pages, 7 pages, statistical analysis, and so on. Then you see actually according to the frequency who plays what. So that's fairly simple and easy break. So here is a very simple illustration of one of the famous methods. It's called RSA method. It appeared in the early 70s, and actually I remember when that appeared, it was a huge triumph for the number theory, because number theory was always in mathematics considered as being very elegant and interesting, but never applicable. So it's like for our fun, we are doing number theory. Since that moment, number theory became a very, very important tool for applications, for encryption, and so on. So it got that applicability part in that branch of mathematics. So I will just illustrate in a very simple way how the idea of RSA method with very small numbers, so that you can get the main idea. Actually, this will be a very important decryption method. Yes.
Every summer at Santa Barbara, they have a crypto conference.
Uh-huh.
And I remember that when I transferred in 2008, they actually had the RSA guys, the guys who created it there.
All right.
That was pretty cool.
Sadelman and Shamir.
Yeah.
That's where the name comes from. Okay. Great. So, let's see how the method works. First, let's record this fact, because I will need it later on. So let's record this fact so that we have it on the side. For whatever reason I might need it, I will record discussed this question a minute ago? How to find the inverse. So I'm doing the following. For whatever reason, in the moment when we start doing something, I will need modulo 72 to solve this equation. Does this equation have a solution? Yes, because 5 and 72 are relatively prime. Do I know how to get it? Do you clean the algorithm, recover it backwards as we explained? When you do all that, you will get x equals 29. Clear to everybody? So what? So how is that working in the following encryption problem? Or decoding? So here it is. Apple says the following. Someone coded a secret digit between the 1 and the 94. So there was a digit A, and I know that A is between 1 and 94. But I don't know what it is. And by the way, this whole method of encryption is called public key method where actually everybody knows how I did the coding, not Caesar. Method, everybody knows what we are doing, but they still cannot break it. And you'll see in a moment why. So generally, here's how the encryption was done. So someone took that A and raised it to the power of 5. All right, someone took A and raised it to the power of 5. And then reduced it modulo 95. And he got the result of 27. So that's the coded message. So that 27, so word A was original word, so it's like and 27 is the coded word. And 27 is being sent to insecure channel. And now the question is, how can we decode this word now? How can we get our secret word A backwards? So when I raise it to the 5th, I get 27. How can I get A itself? So what are we going to do? I want to use this theorem here. And what is this theorem here? 95 is 5 times 19. You agree? So are they both primes? So this will be P. And if I use this version of Fermat's theorem, we'll get the following. We know the following. That A to what? 4 times what? 18. Because Q minus 1 is congruent with 1 modulo what? And be careful, there are 2 congruences here that are important. One is, I call this